Hi there, I'm on my way to pick up Pindi so that we can go in search of everyday optical instruments that uses lenses. While I'm going there, you can take a look at the outcomes for today's lesson. By the end of today's lesson, you should be able to describe how microscopes, binoculars, and refracting telescopes magnify objects. Hi there, Pindi. Are you ready for this field trip?
Yeah, absolutely.
Get in.
So where are we going?
Well, I thought we'll start off small.
Small?
Yeah, small, with optical instruments that help us see things that are too small to see with the naked eye.
Oh, you mean microscopes?
Yeah, that's right. We were going to the University of Johannesburg lab to speak to Cherie about microscopes. Actually, now that I think of it, we have already looked at a microscope in this series.
No way.
Really? Microscopes, in one form or another, have been used for about 3,000 years. The earliest types were very simple magnifiers made of water-filled glass bubbles or chips of transparent crystal. The very first lenses that people used in primitive eyeglasses were manufactured in Europe and China as early as the 13th century. By this time, most glass cutters had already figured out that if you ground most clear glass or crystal into a specific shape, generally thicker in the middle than at the edges, it would produce a magnifying effect. All single lens magnifiers are called simple microscopes.
Okay, so the microscopes that you were talking about when you said that we've already seen one in this series is the magnifying glass that we saw in lesson 1.
Yes, that's right. Wait, there's something I want to show you. There it is. Remember I was telling you about simple microscopes? Now, in the 17th century, a man called Anthony van Leeuwenhoek took constructing magnifying glasses to a whole new level. Leeuwenhoek was an extraordinary lens grinder. He manufactured minute magnifying lenses, some as small as a pin head, with very short focal lengths that achieved magnifications of up to 500. Remember, magnification can be calculated by dividing the size of the image by the size of the object. Using his very small lenses, he observed tiny animalcules, what we know today as bacteria, for the first time.
No, but wait. If I remember correctly, a convex lens only acts as a magnifying lens if the object is between F and the lens. So how on earth did this man use something so small with such a short focal length to see anything?
With great difficulty. Because of the very short focal length, Van Leeuwenhoek's small lenses had to be held only millimeters from both the object and the observer's eye. This is the biggest limitation of single lens magnifiers. The microscopes that we've come to see today are called compound microscopes, and they were designed to solve the practical limitations of simple microscopes that we've just pointed out. Can you think why they're called compound microscopes?
Well, something is called a compound when it is made up of a combination of things. Does this maybe mean that these microscopes are made up of a combination of lenses?
Yes, that's right. The simplest compound microscope uses a combination of two lenses. I'm sure there's a diagram in here that shows us how it works. A simple compound microscope uses a small lens with a very short focal length. Here, this is called the objective lens. The object is placed here, close to the lens, and forms a large inverted and real image here. A second converging lens is used as a magnifying glass to make the image even larger. No one knows for sure who invented the first compound microscope, but it is reported that Galileo studied and described the eye of an insect through a two-lens microscope in the 16th century. Now that we know the basics about microscopes, let's go and find out how microscopes have evolved since Galileo's day.
Hi!
Hello.
You understand essentially how a microscope works, right?
Yes, I think so.
Well, let's keep it simple then. This is a school lab microscope that you would have used in your biology classes before, okay? And this is where the objectives are. As you can see, there are 3. And this is where your eyepiece is. We place a slide on the stage, and then this is how you can view a slide. Take a look.
Oh, wow, that's incredible. But can you tell me, why is there a mirror underneath the slide?
It's simply so that we can focus the light so we can get the sharpest and brightest image possible.
I don't think I quite understand.
Okay, remember, an object only gives off a certain amount of light, okay? So what happens is then, as the magnification increases, the same amount of light is increasing with that, and the object gets dimmer. So what we do is we substitute a mirror to add more light, and that way the object is better focused.
Let me see if I can explain it in another way. Imagine that you're buttering your toast at breakfast. A level teaspoon of butter will probably give you a nice thick layer of butter on your bread. But what if you don't live alone? As well as your brother and 2 sisters, you have some friends staying with you. If you used the same amount of butter to butter a slice of bread for each of them, there would be hardly any butter on each slice, and they probably wouldn't be able to taste it. If you are all to have a nice thick layer of butter, you'll need to add more butter. In the same way, if you want a nice and clear magnified image, you need to add more light.
Oh, I see. By using the mirror, you are reflecting more light onto the object. And this makes it possible for more light to come from the object. And this means more light moving to the image. Just like with more butter, you would get a thicker spread per slice. In this case, it means you'd get a more clearer magnification.
Exactly.
You said that simple compound microscopes use 2 lenses. Does this mean that there are microscopes that use more than 2 lenses?
Oh yes, most definitely. As you can see, this is an inverted binocular microscope. It has 2 eyepieces and 3 oculars, but the light is inverted at a different angle. Therefore, we get a better resolution on our pictures, and this microscope is commonly used for cell cultures.
Well, we have to be off, but thank you very much for speaking to us.
It was a pleasure.
Okay, thank you.
That was great. Where are we off to next?
Next, we're off to Louis Barense, who is going to tell us all about refracting telescopes and binoculars.
Cool. I've always wanted to look at the stars.
No, before you get carried away, I want you to think perfectly about how binoculars and telescopes work, scientifically speaking.
Well, I've been thinking about your question, and I don't know how scientific this is going to sound, but I'd say that a telescope is used to look at faraway objects. And what it does is that it makes the objects appear as if they are much closer than they actually are.
That's absolutely correct. Another way of putting it is that telescopes and binoculars are used to magnify distant objects. Oh, there comes Mr. Barense. Mr. Barense, can you please tell us where the idea of magnifying distant objects with the use of lenses came from?
Oh, this is a very old idea. It started in the early 1600s by a Dutch fellow, Hans Lippershey, and he made a first little telescope. Today we would know that as a pair of opera glasses. And he tried to sell this thing without a lot of luck, but Galileo saw it and thought if he modifies it a little bit and makes it longer, he'll get more magnification. So he made the first, what we would call an astronomical telescope today, something like about a half a meter long and 25 millimeters in diameter, with a big magnification of 3 times. And he used this telescope to start looking at the stars, and he actually saw the moons of Jupiter with that tiny little telescope that he made.
Can you tell us more about the actual design of this astronomical telescope?
Well, it's actually a fairly simple thing. We need a large lens to collect lots of light, which is going to make a little image somewhere. And then what you do is you have an eyepiece, we call it an eyepiece, which is like a magnifier to look at that image. And then you create another one which we call a virtual image.
We've learned that magnification can be calculated either as image size divided by object size or as V divided by U.
Do you use the same calculations for the magnification of telescopes?
Well, for a telescope, because the object is so very far away, it's very difficult to measure the size of the object, so you can't really do it that way. So for a telescope, we take the focal length of the main lens and divide into that focal length the focal length of the eyepiece. Now, the longer the focal length of the main lens, the larger the real image is that you're going to get. Okay, the focal length of the eyepiece, the shorter that is, the more magnification or the more it will magnify an object. Now, if we look back at old pictures of telescopes, we'll see some of them got really long. They mounted the main lens on a pole very, very high up, and they had all sorts of ropes and things to move it. So they got rather big. But if your lens is too small, you don't get a lot of light. And the more you magnify it, the more you spread the image out. Okay, the same as your bucket. If it's got a big opening on the top and it's raining, it collects more rainwater. If you've got a tiny little hole on the top, it only collects a little bit of rainwater. So that's how you collect more and less light with a telescope.
Oh, just like the butter example you used earlier.
Yes. So, for the telescope to be able to have good magnification and a bright image, you need as much light as possible. Isn't that right, Mr. Parense?
Oh, absolutely. If you want to really see the faint things in space, you really want a big telescope. So with astronomy, the bigger the telescope is, the better it works. Now, if we look at these telescopes here behind us, in the real astronomical world today, they would be called tiny telescopes. Wait, I'll give you an example. I'll show you with a magnifying glass. We'll use a large and a small magnifying glass, and we'll burn a little hole in paper, and we'll see just how quickly it works. Now, these two lenses will have the same focal length, so we'll get the same size image. And you will see the little one will take a long time before it starts burning the paper. And now if we look at the big one, we see that it burns rather quickly. Okay? So there is more energy in the little image of the big lens than in the little image of the little lens. Do you understand how this is working?
Yes, I do, thank you. What I don't understand is where binoculars come into the picture. I mean, if we can use telescopes and they give us such great magnification, why not just use them every time we need to see faraway objects?
There's another little problem with the telescope. If you guys remember from the design of the telescope, the image is going to be upside down. So we're going to have to correct that. It's very difficult to watch people when they're running upside down. The balls will fall up instead of down. These are serious problems. Also, imagine sitting at the rugby field or the soccer field with a long telescope. As you turn around like this, you're going to bang everybody on the head. So that's not a good idea. What we have to do is fold this thing and make it shorter and turn the image the right way up. And that's what we do with binoculars.
Now, remember what you've learned previously about internal reflection. Using prisms, it's possible to change the direction a ray of light travels in, like this. Light enters here, is totally internally reflected here, and leaves the prism in this direction. If we were to use 2 of these, then it would enter the second prism here, and again be totally internally reflected here and here, and then emerge in the same direction as the incident ray. This is exactly what happens with binoculars. Using this design means you can have a long focal length for the objective lens in a quarter of the space. Here's the objective lens, and here's the eye lens. Much easier to hold and handle.
Yes, Gugu, that's right. Binoculars are a lot better, and they do turn the image the right way out. Makes us really happy. Now, the other thing that happens when you have 2 little telescopes is you satisfy both eyes, and your brain is happy because it doesn't have half of its energy wasted trying to say, other eye, please see something. Okay, lots of energy goes into that problem. So your brain is kept happy. But because we have 2 eyes, we can see depth, because our brain merges the 2 images. And from that small distance between your eyes, you can actually measure the distance to things. So you see things in 3 dimensions. If you're using a pair of binoculars, that happens as well.
How would I know what the magnification for binoculars is, and what would be the best size to buy?
Well, that's quite easy. Fortunately, all binoculars are marked with some numbers. Normally 8 by 60 or 10 by 60 or 7 by 50. Now, the smaller number tells you what the magnification is of the binoculars. The 50 will tell you the diameter of the main lens of the binoculars. So the 50 tells you how much light it collects, and the small number, the 7, tells you what the magnification is. Now, if you want to look at stars, for instance, you would buy typically a 7 by 50 pair of binoculars. Okay, that's a good one to buy because the magnification is not too high, because you must remember as the magnification goes up, you're going to shake a little bit more, especially if you're looking up at the stars. Okay, your arms get tired and you're going to shake. So you don't want too much magnification. You get bigger ones. You get 20 by 80 or 20 by 100 millimeter binoculars, but they're not going to fit in the cubbyhole of your car so easily. So I would recommend you buy something like a 7 by 50 pair of binoculars for looking at stars.
We've now talked quite a bit about the ideal magnification for binoculars. What about telescopes? What is the largest magnification for the refracting telescope?
With refracting telescopes, we have about a maximum magnification of 120 times. And that's for a whole lot of reasons, like our atmosphere and the glass quality and things like that. The largest refracting telescope we have in the world is the Yerkes telescope in Wisconsin in the United States of America.
Why are there no refracting telescopes larger than this?
Well, one of the big problems with large telescopes is the weight of the glass. Glass bends quite easily, and the only way you can support the lens is around the edges. Now, if you don't believe me, glass bends, just walk up to a shop window and give it a little press with your finger and you'll see the reflection will move quite dramatically. So glass bends quite a lot. The other nasty with large lenses is, as they get smaller towards the sides, they bend the light slightly differently, and we get what we call chromatic aberration. Now, you get a red image which focuses a little bit further away than what the blue image would from a lens. Now, the bigger the lens, the worse this problem gets. So when you look at the moon, you don't want to see a very large red moon and a slightly smaller red moon, so you've got to try some other tricks. Now, you can try and fix it by putting in more bits of glass, but then it gets heavier and longer. So we move on from there.
There you have it, straight from the expert. But now we have to go straight to Joburg. Now it's getting late. Thank you very much, Mr. Barrense, for your time.
It was a pleasure.
Thank you. Goodbye.
Goodbye.
Bye-bye. Google, I've been thinking. Mr. Barrense said that Yerkes was the largest refracting telescope. But are there no larger telescopes than this?
There are much larger telescopes, but they don't have objective lenses. But we'll look at those in our next lesson. In the meantime, why don't you try the task for today's lesson?
You go to buy a telescope and the salesperson says that you need one that has a small objective lens with a focal length of 800 millimeters and can magnify 400 times. Work out the focal length of the eyepiece using the equation magnification of the telescope is equal to focal length of the objective lens divided by focal length of the eyepiece. Can you explain what the answer you get would mean for the ability of the telescope to focus properly?
Yeah.